All right, this is a continuation of my first video lesson on dimensional analysis. In the first video lessons, I did explain what dimensional analysis is, what is meant by the dimension of a physical quantity, and then I gave some examples of constants that have dimensions and dimensional variables. If you are watching this video for the first time, please, I will want you to go back and look at that video. It's first video on dimensional analysis. Now let's take some quantities and find and try to derive or write down expressions for their dimension. For example, if I have area, the symbol of area is A. What's the dimension? Area is the product of two lengths. You want to find out the dimension of area, derive the dimensions of area. No, product of two lengths, that gives you L squared. So the dimension of area is L squared. Now volume has a dimension. Volume, the symbol is V, the product of three lengths. Volume is defined as length times breadth times height, and each has dimension L. Dimension of length is this, dimension of this is this, and dimension of height is this. So product of three lengths, that is L cube. Product of that. Now let's look at dimension of speed. Now the symbol of speed is V. You can use a lowercase letter there. Now speed is defined as the distance a body covers over the time taken to cover the distance. Dimension of distance is L and that of time is T. Okay, so which means you can write it as L over T or LT raised to power minus 1 following the rule of indices. Okay, quick, let me just include density. The dimension of density, of course, density is defined as the ratio of the mass of a body to the volume of the same body. So dimension of mass is capital M, uppercase letter M. Volume is L cube. That gives the dimension of density as ml minus 3. Okay, dimension of speed and velocity are the same. Okay, so let's move to the dimension of acceleration. Acceleration has been defined as velocity change of a body over time taken for the change. Now the dimension of velocity, which is same thing as speed, is lt raised to power minus 1 divided by t. That will give me lt raised to power minus 2, or we can write it as L over t raised to power 2. Okay, this gives the dimension of acceleration. Then let's look at dimension of force. F, the force acting on the body is the product of the mass of the body and the acceleration that is imparted to the body. Now, the dimension of mass as m, and here we have acceleration, so we can bring it to lt minus 2. That gives the dimension of the force acting on a body. Now, let's look at the dimension of work done, or energy. These two quantities have the same dimension. So, let me use the symbol W for work done, and that gives me the product of force acting on the body and the distance moved by the body. So that is F times D. Okay, so the dimension of force is mlt minus 2, as we have here, multiplied by the dimension of distance. Distance and length have the same dimension. So if you multiply these together, you discover that you are multiplying L by L, which gives me L squared T minus 2. That gives the dimension of work done or energy. Okay, let's say power now. What are the dimensions of power? Power is defined as the work done by a body over time taken, or energy over time. That is the rate at which the body used up energy. Okay, so work done, we've already got the dimension as ml squared t minus 2 divided by time t. Okay, this time t has dimension t, so that will give me, simplifying this gives me ml squared t minus 3, because t, this has the power of 1. So the rule of indices implies that when you divide this by this, of course you divide two indices, you subtract their powers. That gives you t minus 2, that is minus 2 minus 1, that gives minus 3. So that gives the dimension of power, And then how about momentum? Dimension of momentum. Momentum is defined as the product of mass and velocity of a body. Okay, that is the momentum of a body has to do with the mass of a body in motion. So the dimension of mass is m, and velocity is lt minus 1. That gives the dimension of momentum. Okay, so we have seen the dimension of a number of physical quantities. So let's take more. Okay, so let's take a few more. The dimension of pressure. How do we dimension what's the dimension for pressure? Pressure, the symbol is P. Pressure is defined as the force that acts on the surface area and normal to the surface area. Dimension of force is ml t minus 2 divided by the dimension of area, which is L squared. By simplifying this, you have the dimension of area, of pressure as L minus 1, T minus 2. So you can write it here, bring it out here, so I can write it out here clearly. This and this. So you can see that by just knowing the definition of these physical quantities, you can quickly find or write down or derive the dimensions of these physical quantities. Okay, impulse and momentum have the same dimension. So the dimension of impulse is same as the dimension of momentum. Okay, so sometimes we may be asked to find the dimension of a constant, like gravitational constant. Gravitational constant, G, we call that gravitational constant. What's the dimension of gravitational constant? Of course, we have from the definition that the gravitational force of attraction between two masses is given by this equation, the gravitational constant multiplied by the product of the two masses and then divided by the square of their. Okay, so with G equals, making G the subject of the equation, we have Fr squared divided by the product of the masses M1 and M2. So from here you can find the dimension of a universal gravitational constant. So dimension of force is ml t minus 2 multiplied by dimension of this r stands for distance. So we can use our usual letter for the dimension of distance L. Since this one is squared, we have to apply the square to L over dimension of mass, which is m, dimension of the second mass, which is m. So I'm having a product of two masses. So this m cancels out this m. So the dimension of G will be given as m, this is m1. When this is taken up, it becomes m minus 1. L1 here multiplied by L raised to power 2 gives me L raised to power 3, then times T raised to power minus 2. So that gives the dimension of gravitational constant m minus 1, L cube, and T minus 2. Now let's take some more. How about the dimension of angular velocity? Angular velocity. Of course, the common symbol for this is the omega. Now, angular velocity is defined as 2 pi times frequency. Now, 2 pi has no dimension. It's a constant, the dimensionless constant. And frequency has dimension of the hertz has the same dimension of per second. That is, the unit of frequency is per second, which is equivalent to the hertz, the common, the one we use for the units of frequency. Now, this per second means t raised to power minus 1. Okay, so which means the dimension of angular frequency will be t raised to power of minus 1. Then we'll also talk about the dimension of angular momentum. Angular momentum. Angular momentum. Angular momentum is defined as the product of mass, velocity, and radius. That is moment of momentum. It's called the angular momentum. Product of mass of the body, velocity or speed of the body, and the radius. That talks about a body that moves in a circle. That's angular momentum. Okay, the mass is dimension m, speed is dimension lt minus 1, and the dimension of radius is l. That will give me m l squared t minus 1. So that gives the dimension of angular momentum. Okay, how about the dimension of torque or moment? Torque or moment. These two quantities have the same dimension, whether dealing with torque or dealing with moment. Now, moment or torque is defined as the product of one force. When the comes to couple, a couple is a system of forces that is consists of two forces of equal magnitude, acting in opposite direction, and their lines of action must not meet, meaning that these two forces will be parallel to each other. So the product of one of the forces and the distance separating the lines of action of the two forces, that's the torque. Now, force is dimension ml t minus 2, then distance is dimension l, so it gives you the same as m l squared t minus 2, which means moments and torque and even work done and energy. These four physical quantities have the same dimensions. Okay, but in reality, they don't mean the same thing in practice. So let's dimension surface tension. Surface tension is a force that acts along the surface of a liquid at rest, and that force makes that liquid to appear as if it's under tension. It's a stretched elastic skin. So surface tension, of course, can use the symbol F for surface tension, okay, or T. So surface tension is a product of force. Surface tension is force per unit length. Okay, dimension of force is ml t minus 2 divided by L, which is dimension of so these cancels are giving the dimension of surface tension as mt minus 2. So can write it here mt minus 2. So I've seen the dimension of a few more physical quantities. Now let's see more of this. So we have gone through a number of more physical quantities, that is deriving their dimensions. Now I want to take more of these physical quantities and then I have to find their dimensions. Now how about the dimension of moment of inertia? Moment of inertia. Moment of inertia is defined as m, the mass of the body multiplied by the radius squared. Moment of inertia, this applies to a body in a rotating body. Now we have the dimension of mass as m and radius as L squared. That gives the dimension of moment of inertia. So once you know the definition of this quantity, you can easily find out their dimension. Now, how about if the drag force? You are told that the drag force acting on the body that is moving through fluid or a fluid is given by the coefficient of viscosity K multiplied by the radius of the body. Let's assume that the body is a sphere, a spherical body moving through a fluid, and the motion will be opposed by the viscosity or the viscous force that acts between the layers of the molecules of the fluid. So the drag force acting on such an object D is given by D. So we have to find the dimensions of K. So K, making that subject of the equation, becomes the drag force over the product of radius of the spherical body and the speed of the body. So the dimensions of force is m L t minus 2 divided by dimension of radius as L and then speed LT minus 1. So this one we cancel out this, and then so that you have here m. Now when this L raised to power 1 moves up, becomes L minus 1, and when you apply the law of indices to evaluate t minus 2 divided by t minus 1, that gives you t minus 1. So that gives the dimension of drag force, dimension of the constant K, m L minus 1 t minus 1. Okay, so let's take this dimension of specific heat capacity. How do you dimension specific heat capacity? Heat capacity is a symbol is C. Okay, so it's defined as heat energy supplied to the body. Q stands for heat energy over the mass of the body times the temperature change of the body. Okay, so the dimension of energy already, we have got that before now. That is this minus 2 divided by dimension of mass, that is m. Dimension of temperature, we use theta. I know some authors use K for dimension of temperature. Okay, I'm using theta for dimension of temperature. So this is this. So that the dimension of specific capacity gives you L squared T raised to power minus 2 theta raised to power minus 1. That gives the dimension of specific heat capacity. Now let's look at the dimension of electric charge. Electric charge Q, the dimension is defined as this product of current and time. The dimension of current is I and that of time is T. So we have IT as the dimension of charge. How about the dimension of a potential difference between 2 points in an electric circuit? The work done, potential difference V between 2 points in an electric circuit. Okay, and that is defined as work done in moving unit charge between the 2 points. So the dimension of work done for mechanics is m L squared T minus 2. Dimension of charge is current times time. So when you evaluate this using lots of indices, this is T raised to power 1. When I divide this T raised to power minus 2 by T raised to power 1, that will give me T raised to power minus 3. and then this I goes up, so that I have the dimension of potential difference as m L squared t minus 3 and I raised to power minus 1. That is when this the dimension, when this I moves up, it becomes the power becomes negative. So that gives me this t minus 3 I raised to power minus 1. That is the dimension of potential difference. Now, electric potential too will have the same dimension as the potential difference, whether it's electric potential or potential difference. Now, how about the dimension of resistance? How do we dimension resistance? Resistance is defined as the ratio of potential difference to current that is passing through the resistor. Potential difference between the terminals of the resistor or the current that is passing through. So we've already have the dimensions of potential difference as this. So bring it in here. We have this raised to power I raised to power minus 1 divided by the dimension of current, which is Ti. And we evaluate this, so we have dimension of resistance as m L squared t minus 3 and I raised to power minus 2. When you apply law of indices to evaluate I raised to power minus 1 by I, it gives you minus 2. That gives you the dimension of resistance. How about the dimension of current density? Current density, simple is G. Current density is defined as current through the surface divided by the area of the surface. Okay, so dimension of current is I, area is L squared. That gives me I raised to power minus 2 as the dimension of current density.